Hello, Wave Optics, Important Question Part 2. Why coherent sources are required for sustained interference? So, coherent sources are those sources, two or more sources, which produces wave, which emit wave of constant amplitude, same frequency, and constant phase difference. Same amplitude provides good contrast between bright and dark fringes. Constant phase difference supported by constant frequency keeps phase difference constant and hence pattern interference pattern doesn't change. Well, actually, if this is the first wave and this is the second wave, so if their peaks match, intensity will be higher, and if they meet out of phase, then intensity will be lower. So this is explained by this point. If same amplitude provide good contrast, so if they have same amplitude or nearly same amplitude, so either they will get much larger or they will just cancel each other. So perfectly bright and perfectly dark fringes can be observed. So there is a perfect contrast. And second thing, the phase part. The phase part, we know that the equation, I am using this portion also. The equation is sine or cos, whatever. I'm using cos omega t and cos omega t plus phi. Now, if frequency would not be constant, then the difference between these phase terms would no longer constant. So that is why, in order to keep this phase constant, first this additional phase must be constant or zero, or and the frequency term must be constant. State principle on which working of optical fiber is based. Well, I included it here because actually it is taken from some exam paper, and in that these both questions were together, part A, part B. So that is why I had put it here. State principle on which working of an optical fiber is based. Okay, so the principle is TIR, total internal reflection. So during denser to rarer refraction, if angle of incidence is greater than critical angle, that is I is greater than IC, then the ray returns to the same medium. Where sine IC, actually in order to explain IC, 1 upon refractive index. So also we can explain about critical angle, but it is not actually questioned here, so I'm leaving it as it is. Otherwise we can write critical angle is that angle in okay, so entire setup is same. So d by d, actually it will look like this: d lambda 1 over d upon d lambda 2 over d. Rest of the term will get cancelled, lambda 1 upon lambda 2. Now we can put the values. So for first, actually it is written in a, I don't know, just in order to shorten this statement I used these terms. It is looking like double slit is this one apart. Actually fringes are consecutive fringes, bright fringes or dark fringes. Okay, 7.2 mm apart. All right, so beta 1 is 7.2. No need to change its unit because mm will get cancelled, mm with mm, so both are in same unit, so no need to put conversion factor here. Lambda 1 640. Here I am writing unit also upon lambda 2. We have to calculate this lambda 2. So if we do some calculation here, 9 8s and 9 9s. So now we will cross multiply it. 9 into 640 upon this one, and then 80s 720 nanometer. And see, this is how we can handle unit also. Okay, so second part, also find minimum value of order n of bright fringe of shorter wavelength which coincides with that of longer wavelength. So we know that for bright fringe, yn bright expression is n d lambda over d. So they are saying that minimum value of order n of bright fringe of shorter wavelength means they will coincide with longer wavelength. Okay, so it is a general condition, like if these are the fringes for shorter wavelength, so their width will also be shorter. So the longer wavelength will have bit broader fringe width. So we can predict that wherever they are coinciding, it must be longer one. I don't know how I am drawing it, but it must be the longer one will be one less than this. So for minimum possibility, n minus 1 maxima of longer wavelength will coincide with n maxima of shorter. So it means I have to use another page. So y longer one, former one is shorter. So yn, all right, yn b brighter n and shorter is equal to yn minus 1 brighter longer. So this is how I am representing it in the exam. Whatever be the better way you have to express this, go for it. But I think this is something which is explaining everything. So n d, we had put it as, marked it as lambda 1. Yeah, of course, lambda 1 upon d is equal to n minus 1 d lambda 2 over d. So everything else will get cancelled except n and lambda 1. Lambda 1 is 640, lambda 2 is 720 nanometer. Purposely I am writing it, actually not required. So nanometer will get cancelled. So when we remember this thing, when same type of quantities are on either side of equality sign, then no need to change their units. Or if you want to go for it, no problem. But instead you can write unit on both sides and it will get cancelled. So now, okay, we can divide it with the 0 0 will get cancelled, then 8 8s are, so it will be 8n then, and it will be 9, so 9n minus 9. So finally it will go here, it will go there, n equal to 9. Okay, yellow light wavelength 6000 angstrom, illuminate a single slit. Okay, single slit, whenever single slit term comes, just think about diffraction of width. All right, calculate distance between two dark lines on either sides of central maxima. Actually they are asking about width of central maxima. Watch my video in which I have shown the demo of diffraction pattern by a pinhole. So it looks like this, a bright region and then a dark region as a circle, and in that circle what happens actually, the position of this bright region, if this is the slit, position of this bright region is also the width of central maxima. So indirectly they are asking about um, width of central maxima. And remember, half linear width of central maxima is given by d lambda over d. It resembles with fringe width of interference, but it has quite different meaning. So, but here it is for half linear width, and they have asked for two dark lines. Distance between two dark lines means full linear width. So, first point, distance between two dark lines on either side of CM, that is linear width of central maxima, and which is 2d lambda over d, and directly we can put the values. It is 1.5 meter away, lambda is 6000 angstrom, so it becomes 6 into 10 to the power minus 7. I have converted it, you can also do it. It is 6000 into 10 to the power minus 10 meters, so I am directly putting it here upon 1 into 10 to the power minus 4. So if we will solve this, it will become 3 6 are 18, it will go up and it will be 18 into 10 to the power minus 3 meter. You can leave the answer as it is, or if you like then you can write it 18 mm. Okay, next, angular spread of first diffraction minima. It means they want angular width. They have asked for angular width. So angle, this angle they are asking about angle. So angle equal to arc upon radius. So I am writing it alpha. In few books it is also written as 2 theta. Why 2 theta? Because this half is theta. So that is why. Don't go into it. Just focus on whatever I am saying. It is a very short distance and it is a very long distance. So it almost look like arc, angle equal to arc upon radius. So angle equal to arc, we will use this linear width of central maxima upon the distance. So what else we can do here? Actually, if this question would be asked directly, then we could place this value here and dd will get cancelled, then 2 lambda upon d, and we can solve that. But here we have already solved it, 18 mm. Directly we will put it here, Actually in meter we will put it here, and upon 1.5. So it will be about 12. Yeah, of course, 12 into 10 to the power minus 3. Now the answer will be, because it is angle, and when we use angle equal to arc upon radius, then answer is in radian. Okay, a parallel beam of light 500 nanometer falls on a narrow slit, and a resulting diffraction pattern is observed on screen 1 meter away. It is observed that first minima is at a distance of 2.5 mm from the center of screen. Find slit width. Okay, so here this point, it is observed that first minima is at a distance of 2.5 mm from the center of screen. Like, once again I will draw it in this way. This is first minima, actually central maxima, and they are asking about, they have given the value from center of screen to minima. So they have given actually the half linear width of central maxima. So half linear width of central maxima, we generally write it, I generally write it y. So y equal to 2.5 mm. Okay, find slit width. Y equal to d lambda over d, and now we can directly put the value. Y is 2.5 into 10 to the power minus 3 equal to d lambda. D is 1. Calculation will become easier. 500 nanometer, 500 into 10 to the power minus 9. Actually, I should write 5 into 10 to the power minus 7 anyway. Next time, keep these things in your mind. You can shorten these values. Okay, slit width d. So it will be very easier to find it out. Now I am correcting my, not mistake, but I unnecessarily stretched the things. So 2.5 will cancel 5 two times. 2.5 2s are 5. So I am taking this here and entire this here. So d equal to 5 into 10 to the power minus 7 upon 2.5 into 10 to the power minus 3. That is, I am leaving for you people. Here for a single slit of width a, the first minima of diffraction pattern of monochromatic light of wavelength lambda occurs at an angle lambda by a. Okay, so actually what they have given for single slit of width a. First thing, we use d, they have given a, so we don't get confused with these symbols. First minima of diffraction pattern of lambda occurs at an angle lambda by a. At the same angle, we get maxima for two narrow slit separated by a distance a. Explain. So here we can give mathematical explanation, no problem with that. What they are asking about, first a diffraction pattern, and here it is. So they are asking about this angle, and they are saying this angle is lambda by a. And if we replace this system with interference arrangement, then we are getting these two bright fringes at same angle. So we know, since they have given this, they use the term theta, but I generally use alpha to express this, whatever it is. So alright, I will write theta, it will not make any confusions. So theta equal to, they have given lambda by a. Alright, as we know, it's not looking good here. Since sine theta is equal to sine theta d is equal to n lambda for minima, and here sine theta is approximately equal to theta. D is a given, and n is 1. for first minima. So if we put all of it here, then we will get theta equal to lambda by a. This is the first thing. But there's no problem with this. The problem with the second one. Now, distance between two maxima of interference. Why I'm using the term for interference? Because two narrow slits they have used. So that is why. Distance between two maxima of interference is beta equal to d lambda over d. So here we can write it d lambda over a, because here they have given it a, because separated with a distance. This is not that slit which is used here. Here for diffraction it was a, and for interference this slit separation is a. Meaning is different, but okay. Now the angle. So they are asking about angular width. So angular width. So I don't know whether it will come as theta or not. So that is why this time I'm using some other term. That will be equal to beta upon d. Why? Because angle equal to arc upon radius. This is arc, beta, and this is radius. So arc upon radius, beta upon d. Beta is d lambda over a upon d. D will get cancelled. So lambda by a. It will remain same for second thing, which is we required to explain. Okay, draw intensity pattern for single slit diffraction and double slit interference. Hence, state two difference between interference and diffraction patterns. Okay, so well, it is important because it is a part of that discussion also. So what I am doing, I'm drawing both side by side. Here for interference, here for diffraction. So let us suppose I am drawing it between path difference and intensity. Here also path difference and intensity. Oh, actually I have given very less space, so diagram might distort. So it is lambda by 2, it is lambda, 3 lambda by 2, 2 lambda. That's enough. Lambda by 2, lambda, 3 lambda by 2, 2 lambda. And on other side, it will be in same way. Alright, so in interference, intensity will remain same. So just follow this way. Lambda, 2 lambda. Maxima occurs on these points and minima occur at these half points. And now join. That's all. And for diffraction situation gets changed. Actually it is not diffraction discussion doesn't start from lambda by 2 but from lambda. So at center the intensity is much higher. Then at lambda we find, see here at lambda we find maximum intensity and here we find minimum intensity. And now at 3 lambda by 2 we find maximum intensity but less than central maxima. And again minima and again maxima, but we don't have that much space. But if you would draw, like to draw, if I am drawing it, so that must be less than this. Now you can join. So central maxima, peak of central maxima will look like, because it is much broaden up. So here it is like this. Okay, So to difference between interference and diffraction pattern, first difference is interference, all fringes, bright fringes. Actually, we define the shapes with dealing with bright fringes, and so also dark fringes will come side by side, but all bright fringes have same width and same intensity. But in diffraction, CM has maximum intensity and higher members have continuously decreasing intensity. Second thing, interference pattern has good contrast. Diffraction pattern is dull, means it is not as sharp as interference. What is the effect on the interference fringe in if monochromatic source is replaced by a source of white light? First thing, fringes will be colorful. As yn bright equal to d lambda over d, and individual lambdas will form their own maximas. Second thing, okay, but instead of all of it, central fringe will be white. Central fringe will be white only, because all the waves will reach there in same phase from both the slits, because from both the slits waves reach it with zero phase difference. And you can imagine about this. So no zero phase difference, zero path difference. Path difference. Okay, there is another point we can add on it. We know like violet color has lesser wavelength, shortest wavelength. So afterward, after this I mean central bright fringe is obtained, then first member which will be observed on either side of that maxima will be violet. So first member on either side of central maxima will be violet. This we can add on it. So this is what I have explained you, because all the member will come here, and afterward whatever be the member, because lambda for violet will be shorter, is shortest. So after that, next member will just on the top of, on the edge of that central maximum fringe, and that first member will be that which has shortest wavelength, and violet has shortest wavelength. So first member at the edge of central bright fringe will be violet in color. So this is the third point we can add on it. There is not much space, so I'm just asserting it. I'm reasserting it because violet has minimum wavelength, So just next to central bright fringe, at the edge of central bright fringe, violet maxima of violet will appear. Okay, again diffraction question. In a single slit diffraction experiment, a slit of width d is illuminated by red light of wavelength 650 nanometer. For what value of d will first minima fall at an angle? Okay, this, and first maxima fall at this. Why does the intensity of secondary maxima become less as compared to central maxima? Okay, this is other part, theoretical part. So first, for minima, for maximum, it is not difference between them, but my way to solve it. So for minima, we know that sine theta is equal to n lambda, different thetas, so sometimes subscript n is put here. And for maxima, sine theta, now this theta and this theta must be different, so I'm putting it theta prime n equal to n plus half lambda. All right, so okay, now we'll move further. Now um, oh, one thing I've missed. mm, D multiplied here also, D multiplied. Okay, so generally I write sine theta into D, but this time I have written it like this, but put this multiplication sign also, otherwise it look like differential. So uh, D we have to, okay, the D which will come here will be different and which will come here will be different, so no relation between these two. All right, so D sine 30 equal to first minima into 650 nanometer. So I'm converting it. It is much safer way to express your answers. Sine 30 is 1 by 2, so it will be like this, 1 into, oh, why? Actually, these unnecessary term you need not to repeat again and again. So D equal to 1300 10 to the power minus 9, or 1.3 into 10 to the power minus 6 meter. In the same way here, D sine 30 again, and if we put n equal to 1 because of first maxima, it will be 3 by 2 lambda. Lambda is 650 into 10 to the power minus 9. It is 1 by 2, 3 by 2, 650 minus 9. So D equal to this. So D equal to 1.95. Well, not required, but meter. Oh, sorry. 6 now. Okay, why does the intensity of secondary maxima become less as compared to central? Oh, secondary maxima becomes less as compared to central maxima. So Cm is formed by constructive interference. I use the term superposition of all the waves reaching there. But secondary maxima is obtained by splitting the wavefront over and over. And that's true that other parts of splitted wavefront get cancelled in pair, and remaining unpair gives maximum intensity as shown below. So it is like if AB is the diffracted wavefront, so if we split it into three parts, then this part and this part, they will cancel each other, and this gives the resultant. Now for higher term, slit is still there and this wavefront is still the same, but now it will be higher order term. It will be split into 5 equal parts, out of which these two will cancel, these two will cancel, and this will give the resultant. And in the same way, these two will get cancelled, these two will get cancelled, these two will get cancelled, and this will provide resultant. So over and over, the contributing part, the part which is contributing to central maxima, is decreasing. So in younger double slit experiment, monochromatic light of wavelength 600 nanometer illuminate pair of slits and produce an interference pattern in which two consecutive bright fringes separated by 10 mm, that is beta, this is lambda. Another source of monochromatic light produces interference pattern in which two consecutive bright fringes are 8 mm, beta dash. Find wavelength of light from second source. Oh, so we did such type of question earlier, and unnecessarily I have you know oh, all right, I have left so much space here. So we know beta equal to d lambda over d, so directly we can do beta 1 upon beta 2 equal to, that will be, because same arrangement is there, so that will be lambda 1 upon lambda 2. Now you can put the value, you can get the answer. Alright, here's something special. In young double slit experiment using monochromatic light of wavelength lambda, the intensity of light at a point on the screen where path difference is lambda is k units. Looking little bit annoying, little bit confusing, and the term which we not generally use, but yeah, of course we have to think at different levels in this question. So few things, they have given wavelength, okay, we know. They have given path difference. What are we going to do with this path difference? So if you could remember theory of interference, then oh, there's a problem with focus, yeah, theory of interference, then we know that resultant intensity I is given by 4I naught. Sometimes this entire 4I naught is replaced by I naught, so be careful about that also. 5 by 2. And then we know that for constructive interference, maximum intensity phi should be 2n pi, and there is another term, delta x, path difference, which should be n lambda for maximum intensity for constructive interference. And in the same way for destructive interference, there is another thing. But what are we going to do with this? There's a relation between phi and delta x. First, if as I have written this, so I'm writing for minimum also, and delta x minimum is n minus half lambda. This minimum means for minimum intensity, but the bottom line is phi upon 2 pi is equal to delta x upon lambda, which is important part. So the discussion is over delta x, and if we want to do something with intensity, so we require phi. So from delta x we will find phi, from phi we will find intensity. So this is the order in which we have to go. So case 1, case 2, we will divide it as I usually do. Case 1, delta x is lambda. Case 2, delta x is 2 lambda by 3. So case 1, phi will be equal to 2 pi delta x by lambda, that is 2 pi lambda by lambda. So phi is equal to 2 pi in case 1. So what about the intensity? They have given intensity k, but I have to write its formula also. 4I naught cos square phi by 2. So they have given k. So k is equal to 4I naught cos square 2 pi by 2, that is cos pi, and cos pi cos 180 actually, and cos 180 is -1. If you don't know about it, so follow this pattern: cos 0 1, cos 90 0, cos 180 -1, cos 270 0, cos 360 1. All right, so cos 180 -1, because it is cos 4I naught cos square pi, cos pi is -1, so -1 square means 1, that is 4I naught. K is 4I naught. Now here, with this, phi is equal to 2 pi delta x. In the place of delta x we have 2 lambda by 3 and whole upon lambda, so it will be 4 pi by 3. So now I is equal to 4I naught, where we will put k later on. Cos square phi by 2 means 2 pi by 3 by 2. Oh my god, 4 pi by 3. Then it will 4I naught, I'm directly putting it k. So it is now cos square 2 pi by 3. 2 pi means 360. 360 divided by 3, that is 120. Cos 120, what is the value of cos 120? It has same value as cos 60, but with negative sign. Why? Because of this. After 90 it becomes negative, but doesn't matter because we have square here. So cos 120 is same as cos 60. There is a mirror image for that. Cos value is 1, then root 3 by 2, then 1 by root 2, then 1 by 2, then 0, and then -1 by 2. It will be, okay, once again we'll put this. So -1 by 2 square, so it will be k by 4. This is the answer. In the same way, here you have the question. So I expect that you people can do it yourself. If any problem, any confusion is there, you tell this question: describe young double slit experiment. It had another part, but I removed that. I'm interested in this only. So how can we describe young double slit experiment? There is a diagram in the book in which it looks like this, and so many concentric circles are there, and again some circles are there, some dotted lines, and some solid lines. So whenever there is an intersection of dotted line with solid line, that is minima, and whenever there is intersection of dotted line with dotted line or solid line with solid line, there is a maximum. But there is a big thing. I'm just stopping it here. We don't require that much working here. We can go very straight in a very straight manner. We can say that a point source made by a single slit illuminates double slit. Which produce secondary waves which superimpose on one another and produces interference pattern on the screen. That's all. It looks like this. This is the source, S1, S2, and wave reach here, and then All other possibilities are there also, but only this much we can draw, that's all. Next, describe how different oh sorry, I forgot my own short form. Describe how diffraction pattern is obtained due to single slit illuminated by monochromatic light. So when single slit is illuminated, it emit secondary waves. So these secondary waves, when superimposed on one another, they produce a diffraction pattern. So there is a plane wavefront here, AB, and it divides into a number of wavefronts, and then final pattern is obtained on the screen. So we can describe it as a single slit is illuminated by a plane wavefront of light. Slit emits secondary wave which superimpose on one another and produce diffraction pattern on the screen. All the waves reaching center of screen have no phase difference with their just opposite component. Hence, interfere constructively. Constructively and produces central maxima. So this is how this diffraction pattern is obtained by the superposition of secondary waves. Why central maxima is bright? Because all the waves come here and just opposite one, this one, opposite this one, anything else which is coming from here, it will have just opposite component, and that component and these two together produces, they both have no phase difference, so they constructively interfere and produces a maximum intensity which is called central maxima. There are some descriptive questions. I'm not going to answer them. I will just tell you what to answer, how to give its answer. Later on in another video, I will not explain, but I will just write these answers. Otherwise, video will become very lengthy. So using Huygens construction of secondary wavelets, explain how diffraction pattern is obtained on screen due to narrow slit on which monochromatic beam of light incident normally. Show that angular width of first diffraction fringe is half that of central fringe. Explain why maxima at theta equal to this become weaker and weaker with increasing n. I can answer all of them, but I'm not going to write it here. So how diffraction pattern can be explained using Huygens principle. So the idea is somewhere here. So you can write that from slit secondary waves emit and they interfere one another to produce diffraction pattern. Second thing, entire diffraction pattern, all the discussion based upon that, you have to do that. All right, so this thing you have to do it as you can see the concerned video. I will put its link in the description where I have derived entire it. And this thing, why it becomes weaker and weaker, and I have given its answer earlier also, that the diffraction maxima we explain by splitting diffracted wavefront, and as we go for higher members, as we increase n, So that diffracted wave front goes on splitting into smaller and smaller wave front, and hence its intensity decreases. Here also consider two source producing this and this. Sometimes they give, sometimes they say that establish the condition, or sometimes they can give you the equation, concerned equation, and you have to derive accordingly. So another this thing, entire this derivation is given in another video, so you can go through it, and it is a straightforward question, nothing is confusing about it. What is the effect of interference fringe when width of source is increased? Okay, so here is something which is not covered in that video. So width of source, so there is a condition in this entire setup, that small s upon capital S is must be less than lambda upon d, where small s is the size of width of um, that point source. Small s is width of point source, that is source slit, and capital S is distance between source and double slit. So now what happens, they have said that width of source is increased. So if s increased, then this condition will not be satisfied, then above given condition will not be satisfied. So interference pattern will be disappeared. Monochromatic light replaced by white light, many times we have answered this. Then fringes will become colorful. Central fringe will be white because all the rays coming there in pair on opposite sides will reach there with no phase difference and interfere constructively. So all will mix together and form a white central region. And third thing, violet color will be found at the edge of central bright fringe, because violet has least wavelength. So for next member of bright fringe, it will be close to central bright fringe, according to formula y n for bright d lambda over d. So because of low value of lambda, it will not at higher position, means next bright member of violet. Because of less lambda, it will be close to that bright region in the middle. Means if for other members there will be their next maximum fringe, bright fringe, then violet must be at the bottom of it, that is close to central bright region. So here again same thing, but with sine waves. So again we can derive it and obtain. Okay, one more thing. When we derive, it comes 4 I naught cos square phi by 2. They have given this. It means, so when you will derive, you will find this. So and k also. So 4k square equal to, we put I naught, but here 4 is not there. So it means they have taken entire this term as I naught. One more thing, we generally put this k as a constant multiplied with amplitude square, and generally they will say that directly they can even give it as 4a square cos square phi by 2. It means they have ignored this constant, or they have taken it equal to 1. So don't get confused with, if you will find anything else here. So just understand the concept that okay, they have absorbed entire other terms into this. So you can find equation like this, you can find equation like this, you can find equation like this. In fact, you can find equation like, as I told you, this. So don't get confused, just focus on this part only, and this you can just adjust according to whatever given in the question. All right, this one I'm not going to solve it, but I'm just explaining its diagram. So they have asked for plane wavefront reflecting at the interference of two media. So for reflection, what you have to do, there is a reflecting surface and just incident. So the derivation, concerned derivation is in other video, so I'm not going for that. Here we can do a trick, and okay, I will give its tricky way. So I'm just cancelling it. I'm just concerned with its diagram. So how can you draw its diagram quickly? So I will let you know about that. So this time I'm using scale. So we can use directly by hand, freehand drawing, but this time it will save your time. Just put it at very acute angle. This angle must be very acute, and now put it on these 2 points, and that's all. So this is okay, this is incident wave front, must be perpendicular to each other. Yeah, so this is incident wave front AB, and this is reflected wave front B dash A dash, and angle of incidence I, angle of reflection R, and if it is I, then entire this is also I. If this is R, entire this is also R. And one more thing I missed is an arc, because this has spread till this point A dash. In the meanwhile, from this A point, waves will emit in the same radius, that of this BA dash. And remember, this will not cross this limit. See, this is a right angle triangle, so hypotenuse will be the maximum. So this side, if we take the length of this side and then draw arc, then it can't be lengthier than this hypotenuse. So it must pass from somewhere here, and it have to touch this point. This is how you can draw, and you'll get full marks for that. For refraction, that is Snell's law, we don't require scale to draw. So here diagram is much easier to draw. Okay, it is not given that whether denser to rare, it is denser to rarer or rarer to denser. So I am going to draw both of them. So for if it is rarer and it is denser, then remember, in denser medium, speed of light is slower. So the time in which B reaches B dash, that is distance equal to speed into time. So if here speed is v1, so this distance is v1t, so it will spread into little bit lesser distance. So let us suppose, so if we take arc, reduce this arc, because it will not spread into this radius, it will spread to little bit lesser radius. So somewhere here, this thing here, draw tangent, or you can first do this and then afterward you can do that. So this is how angle of incidence and R. So this is R, if this is I, this is I, and that's all. Yeah, of course, this A dash, this will be V2T. So nothing more I'm doing here, nothing more, nothing less. That's all in this video. Still a few more things to be discussed, but I want from here hear from you people that if you face any trouble, any doubt, any confusion in any topic or any question, you can write me in the comment. Bye bye.